So our new friends who walked in and left the door open, I have a question for you. What was the first question that you answered? What? No. Okay, what about the second question? What? What's a busy weight? No, busy weight. What? Yeah? That's calibration. Perhaps calibration, that would be a nice definition, but not busy weight. Who's the newcomer here? Who have just arrived? What's a busy weight? You know busy weight? Can you tell them what a busy weight is? Listen to the answer, guys.
It's like a continuous weight.
It's continuous weight with using resources, with using the CPU. We're continually checking something. Is it on? No. Is it on? No. Is it on? No. You're waiting for it to come on or off or whatever it is. Or maybe a critical section. Is it free? No. Is it free? No. Continually checking. Is it free? And that uses the resources. We call that busy wait. That's a bad way of waiting. And we looked at three mechanisms that control critical section. And you know what a critical section is? Yeah? It's part of the code of a program that if it's executed by more than one process, it might cause a problem. So we try to protect it. That's a very sensitive part of a program that can cause problem if it's run or executed at the same time by more than one process, or two or three, depending on the situation. So we call that critical section. To protect critical section, anybody knows one technique used to protect a critical section? What? Spooling is actually to prevent a deadlock. Remember, we have separate problems when multiple processes execute. We have deadlocks, we have critical section problems. Now I'm talking about critical section. Okay, let me ask you about the deadlock first. How do we avoid a deadlock? Pardon? Eliminate one of the four conditions. A good answer. That's the wrong answer. That's how to prevent a deadlock. I'm just saying this, repeating this, because a lot of students lose a lot of mark in the exam because of this. They say, how do you avoid the deadlock? And you start telling me how to prevent it. Or I say, how do you prevent it? And you start talking about how to avoid it. A deadlock is prevented by removing one of those four conditions from your system. Then you'll never have a deadlock. That's prevention. Avoiding, it's possible that you might have a deadlock, but we keep avoiding it. And that's using Banker's algorithm. Okay, but my question wasn't on deadlocks. My question was on critical sections. How do we protect critical sections? The idea? Techniques to protect critical section. Maybe now you can tell us one technique is to protect critical section. You know? Test and set is one mechanism. Any other mechanisms? That's an old mechanism, has a couple of problems. Any other mechanisms to protect a critical section? Wait and signal mechanism, or the semaphore mechanism. Okay, look at those, guys, look at those. We looked at last lecture's video. All right. Today we're going to talk about device management, device manager. And specifically, we're going to be talking about two main devices, tapes and hard disks. So it's hard disks really. Most of we'll concentrate on hard disks. Let me remind you again, I put a message on Moodle reminding you that we have a class test coming up soon. Has anybody seen that note? No? Oh my God, okay. Class test, we have a class test on the 26th of April. That's in 2 weeks' time. Okay, just so you won't be surprised in 2 weeks' time. Like I've been telling you about this for a long time, but it's definite. It's on the 26th of April on a Tuesday, but it's going to be a sunny day, not like today. It's going to be a beautiful day. And we'll have a class test. You'll probably have a question on from every chapter we had so far. Right. Is anybody on Zoom? Close the door, please. How do you say close the door in? Yeah. Is anybody on the Zoom? Okay. All right. Now we're going to be talking about device management. Anybody, before we talk about it, knows anything about it? Just a quick question. What are the responsibility of a device manager? Keeps an eye on all the devices. Anything else? Device manager, what does it do? Allocate devices to users. Great. So you know a lot about device management already, which makes it a lot easier. So let's get along. Let's keep moving. Right, we're going to be look at different devices. We already know, first thing we're going to be learning about the dedicated device, the shared device, and virtual device. You already know that. We've already mentioned that many times. Anybody knows the difference between a dedicated device, a shared device? Just tell me, what's a dedicated device? A device that's used by a single user. Good answer. That's the wrong answer. What's a dedicated device? At the what? At the same time. This is not simultaneously. Only one user at a time. Right. Because a printer is a dedicated device. 20 people can use it, but not at the same time. That's the point. It's important to know. It's not just one user. Right. And what's a shared device? The opposite of dedicated device. What's a shared device? It's a device that can be used by any number of users or more than one user at the same time. It's important to put simultaneously or at the same time. What's a virtual device? Do you need to be turned off? No? Okay, no, sorry. Were you gonna answer? A virtual device? No? Yeah? Exactly, a virtual device, thank you, is a dedicated device, like a printer, but we can share it. Or appear like we are sharing it. We know we can't really absolutely share it in reality, but that's why we call it virtual, almost. Okay, and we look at differences between sequential and direct access devices. A sequential device is a device that when you take information from it, you have to take it in sequence. Direct access, you can directly go to any place you want, without having to follow a certain route. So let's move in, and then we'll talk about hard disk. We'll look at more details. We'll take a detailed look at hard disks, and then reading from a hard disk. If you have 10 requests to read from a hard disk, how would you read them? What's the policy to get the best performance, the quickest read or write operations to a hard disk? We need to do all this today, if we can. Because I think next Friday is holiday, and Monday is holiday. Did you know that? Okay, now you know. Friday and Monday. Okay, so if you work somewhere on a Friday or a Monday, maybe you should get double pay normally, but how are you today? Are you okay? Where is your friend? Did you get rid of her? Okay, I'm only joking, it's okay. It's okay. Okay, so device management, guys, tracking the status of every device, that's the responsibilities of a device manager, to track every device connected to the computer. Because all devices are under the control of the device manager, who represents the operating system with devices. He needs to know at all times, what do we mean by tracking? What device is there? Is it available or not? Is it operational or not? And is it being used right now or not? And if it is, who is using it? So it needs to know a lot of information about each device. And then the device manager will allocate and deallocate based on policies. The policies are set by the system administrator. Maybe two processes want a device. Who should the device manager give it to? Could be maybe the more important, the higher priority process, or the one who needs it for a shorter period of time, and so on, as we've seen before with CPU management. It's reasonably similar, but there's a bit more, speciality here. Right, types of devices. Devices can be categorized by many different ways. We can say, what are the different types of devices? Well, it depends. Maybe based on usability. Is it shareable, or is it dedicated device, or is it virtual? Like the different categories. Or based on the characteristics of the device, or maybe based on the speed of the device. We looked at dedicated devices. They are assigned to one job only at any given time. The problem with these, they must be allocated to a single user for a certain length of time. And they can be quite inefficient, especially when device is not used 100% of the time. So dedicated devices really a problem, and they can actually lead to deadlocks. That's really the first thing that in a system that will lead you to a deadlock if your devices cannot be shared. Because if one user is using it, another user wants to use it, it's busy, they have to wait. Once you start the waiting, then you're going towards a deadlock. But now we're not studying deadlocks. So it's better to have shared devices. Virtual devices is a device that normally is dedicated, but we will use it or turn it into what appears to be a shareable device. One example of that, a very good example, is spooling. And this is really what we've already looked at, spooling. But spooling is, there is a process, we call it the spooler, and that's now everybody talks to the spooler. When they send a request, they print this file. Instead of sending them directly to the operating system that goes to the printer directly, now the request goes to the spooler. And the spooler just says, yeah, of course, I have printer for you, start printing. And you start sending pages or whatever for printing, and the spooler puts it in main memory and tells you it is printing. And what's the advantage of this? Is that the process finishes very quickly. Normally a process sends one line of print to the printer and wait. The printer is a mechanical device, really slow. It takes 1 second or 2 seconds per line. Per page it might take half a minute or a minute. That's way too long for the process to sit. But with this way, we put it in main memory. Main memory is so fast that no process has to wait. Printing happens so quick. When the process thinks printing happens so quick, and it finishes. We tell it, we finished printing, and the process goes and continues or even finishes, complete. And we haven't even started printing its work. Now, the spooler then looks at who's finished printing, and can I send it to the printer? Is that printer finished now? Maybe 5 minutes later it becomes free, and we start printing each process's job. So it's a nice, clever way of making the CPU works quicker, doesn't have to wait for these slow machines. So spooling really has many advantages. It makes the CPU use better, it reduces the delay to all processes, and it makes the printer appears like it's shareable. So it has many advantages. It's a great idea. And it uses buffer. Its disadvantage is that you need memory. You need a lot of buffer. Maybe buffer, it was not available a lot in the old days, but there's plenty of it, reasonably plenty of it nowadays. So it's a good idea to manage those dedicated devices. Now let's get to our main devices. The devices we look at are storage devices, but specifically we'll be looking at the hard disk. But we might as well look at this device here. This is called a magnetic tape, a tape that's used to store information. These tapes were around when computers started, but they only started using tapes much later. Tapes were used by music industry and sound, so they were recording sounds onto it, and humanity discovered how to store sound onto a magnetic medium. So a tape is just a piece of plastic that it's fed when it's still kind of warm or soft plastic. They put a lot of material that can be magnetized. That's iron-based. So basically they put iron powder into the tape and they mix it well and then shape it like a tape. And now you have a piece of plastic that has a lot of iron in it. Why iron? Because iron can be magnetized very easily. And tapes are very thin, so you can have a long kind of tape. You can store a lot of information. And tapes are still, until today, they're the cheapest form of storage. Cheaper than hard disks and all other forms of storage so far. That's secondary storage. Primary storage is main memory. Secondary storage is everything else you store onto the computer or off the computer. So the types of storage devices that we have are either sequential access, and that's tapes, or direct access. That's hard disks and CDs and DVDs and everything that you can go directly to any part of it with direct access. But tapes are called sequential access because you have to start at the start of the tape and keep reading all the way halfway through, or maybe near the end of the tape until you find the file you want. You must do it sequentially. And if you go past the piece of information you want, you can't reverse back to it and start reading. You have to reverse back all the way back and start from the beginning again. So that's really the major problem with tapes. If they did not have that problem, they probably never stopped using them because they're so cheap to manufacture and they are so cheap to use. But the other device is called hard disks. And hard disks are just disks or plates, circular plates of metal that's also covered with or impregnated with iron kind of material that can be magnetized, some kind of material that can be magnetized. So the surface is magnetized. Both surfaces of each disk, the top surface and the bottom surface, and that's another disk, one at the bottom. So they call this a disk pack. It has lots of disks on it. And this disk spins at a high speed, and that's the head. So while the head is sitting there, it can read information off one circle, or can write information onto one circle. We call the circle, we call it track. Then the head can move here or there, anywhere from there. So the head just keeps moving while the disk is spinning underneath it. And there's another image of it. And there's a head on top of the surface. This here, on top of here, there's a head, just like that one there. Down at the bottom part, maybe the head is a little bigger and you can see it. This is an older device. But there's a head on this side and head on the bottom side of this disk. And also a head on either side of each disk, there's a head. And you can read and write on both sides of each of those disks. Tapes are the older, like disks were, first they were introduced or talked about or designed in the 50s, but they weren't used until maybe the 70s, really. So, and when they started first, probably you're able to store 1,000 bytes on a hard disk. As you can see now, we're going to terabytes on a hard disk. That's how much development has been happening. Anybody remember Moore's law? Moore's law? Anybody? Nobody remembers Moore's law we talked about in our first week. Yeah. Thank you. Perfect. Yeah. Every 18 months, since the early 50s, every 18 months, the storage capacity or the processing power or the memory capacity doubles every 18 months. Somebody said it and proved to be true and it's still there. So they call it Moore's law. Right, now, these are what tapes looked like in computer centers many years ago. So there'd be reels here, and this has very long tape around it. And every time you want to use it, a person has to come in and they say, mount the tape. That means put the tape on and put the tape on this side, and this reel is empty, and you take the front of it or the tip of it, rotate it around it until it catches up, and then starts. This one rotates and pulls the tape over. And the tape has to go at a certain speed in order to be able to read or write from it. And the top of the tape, there's a head. I don't know, is there a head there anywhere? There's no head. Okay. There's a small device that has an electric power current that comes, and remember again, I mentioned before that if you have electricity going through a wire, it generates a magnetic field. So if we want to write, we only write ones and zeros of information. So the electric current that goes for 1 or 0 is different, and therefore the magnetic is different. And what we do is we put magnetic charge onto the tape or the hard disk based, and the electric charges are different based whether we want to write 1 or 0. So every time we want to put magnetism on the tape, we send electricity on the wire, and the head is just barely touching the tape. And as the tape is going, magnetism comes in, or the electricity comes in, generates a magnetic field, and turns the particles into a certain north or south direction, and that's for 1 or 0. And again, if we want to read as magnetism, now there's a magnetic on the tape becomes magnetized. That's how we record the music or sound or information onto tapes or hard disks. You put magnetism, magnetic charges on the tape or the hard disk. Now, to pick it up, again, if there's magnetic field and you put a wire in its way, you'll generate small electric current. And that's how we say, okay, that current means 1, that current means 0. So we can actually use electricity to generate magnetic charge and put it onto the tape, or use the magnetic charge on the tape, pass through a wire through it or beside it, and that generates electricity, and we can sense or measure that electric current and write it down as 1 or 0. In the older days, they used papers before magnetic tapes. So when tapes were used, computer science people were absolutely delighted, because papers were so bad, cards, and big and heavy. Magnetic tapes, you're able to store a lot more information and much faster and better than papers, and papers kind of get cut off and all that. So a magnetic tape is used as secondary storage, and when you write information on a tape, you write it in records. You write 1 record, you stop, and the tape is going, so you don't write anything, and then write another record. So when you read, you also can read 1 record and you stop, and then in order to read the next record, you have to start spinning the tape and bring it to a good speed, so the head comes under the head at that suitable speed, and you can read. So in fact, when they wrote information onto tapes, they wrote them in records. And between every record and another record, there is a gap. They call it the record gap. So in fact, a tape has very little information. It's not fully used when they started using it first. So that yellow part is at the data. The rest of it, a lot of space, and then another record, another record. Why? Why do they have the gap, record gap? They call it the inter-record gap. That's the gap between records. Why do they have it? Why do they have such a long gap? Because when you read 1 record and you stop, in order to read the next record, you have to start spinning the tape. And spinning the tape, you need to bring it to a good speed until you can read from it. So this gap gives a bit of space to the tape to rotate and reach the required speed. And then you start reading from it. And if you say read 2 records, then you continue reading. Go to read the first record, go through the gap and read the next record. If you only say read 1 record and stop. So stop maybe just a little bit in front of the record, because even when we say stop, it takes a tiny bit of time to stop. But to start reading, you must bring it up to a certain speed. So they call this the inter-record gap. Also, the inter-record gap is a good way of telling the computer, okay, this is the end of the record. So it's a way of knowing the end of the record and the start of the record. But That's not a good, efficient way. So they started doing something called blocking. And blocking, that means read a block. So what's a block? Number of records, maybe 10 or 100 records. So anytime we ask the computer or your program says, open a file and read one record, it goes to the tape. Instead of reading one record, it'll probably read 20 records and break them into memory and gives you your record. If your program says, read me the next record, we don't go back to the tape anymore. We already have 20 records. We give you the other one from memory so fast. Because if you want to go to the tape each time, it'll probably take a second or 2 seconds for each record. You want to read 1,000 records, it's going to take you 2,000 seconds just reading from the tape. So the tape is slow because every time it's, you have to start spinning and start reading. But this way, blocking, it's like, again, going to the shop. Instead of go to the shop 10 times, you go once, you buy everything, bring it, put it there. Do we need it? Yeah. But sometimes you don't need it. That's the only thing. But it's okay. They found it's a better way to make things more efficient. So when we go to a tape or a hard disk, we never, ever read one record. That's operating systems don't read one record. They always read as many records as they can. They have space in memory. Whatever it takes, for example, it takes 20 records or 50 records. Every time you say, go to the hard disk, go, bring 50 records, put them there. You program, you want one, there you are. With the hope, you might say, okay, give me the next record. But sometimes you don't, and that's okay. We just forget about them and overwrite them. And this is called blocking or buffering sometimes. So if you are asked, what's blocking? It, instead of taking one record, or send in one record, even when we want to write to the tape, you say, can you write this record? The operating system say, yeah, so it's written. In fact, it's not written. It's still in memory. It's in buffer. The buffer can take, say, 20 records. So you say, can you write this record? Yeah, we put them. We tell you they're written. Until your program fills the block. Now we give one command to say, go to the tape and write this block, or go to the hard disk and write this block. It's a lot faster way. Go into a tape or a hard disk. Both tapes and hard disks are mechanical devices. The speed, their speed compared to the CPU, in comparison, is like a horse cart and a rocket, speed of rocket. So you don't want that horse or a cart to use it a lot. Every time you go, it's going to delay you a lot. So you try to go once, if possible. And that technique is called blocking or buffering. Right, let me go back now to the tape. Now, when we write information onto a tape, now we only write ones and zeros. So what do? We don't just write long string ones and zeros. No, we write them across. Every byte is written in one line across the tape. It's like you write one character at a time. If I say, right, maybe you write a message, when we send it one character at a time. Yeah, but every character is 8 bits. How do we write the 8 bits? We write them across the tape. So if it's 1, we put a magnetic charge. If it's 0, maybe we don't put a magnetic charge. Or, we put a different type of magnetic charge. So this is 1 byte. That's 1101 01100. And the last bit here is called the parity. The parity bit is just used as an error detection, just to make sure these things weren't very good at that time. But sometimes we want to put 1, but the magnetic charge dissipates or disappears, so it turns into a 0. So if we say, we use, for example, everything here, in every byte, there has to be 5 1, or odd number of ones, odd. 3 or 5 ones or 7 ones. So we put the parity, the operating system will put the parity, just to make sure the numbers are odd. So if our information that we need to write in the byte, how many ones in this first one? It's 1, 2, 3, 4, 5. Then the operating system doesn't put a 1 here, it puts a 0. So we have 5 ones. That's an odd number. What's about the next one? 1, 2, 3, 4, 5. Also 5. Don't put a 1 here. And this one says put 1, 2. Oh, that's an even number. Let's make it odd. So we put a 1. So the parity, it's put by the operating system or the device or whatever, the party responsible for maintaining the validity of this data. So why? In such a way that every byte has an odd number, for example. So what happens? What if one of these bits disappear? What about if this one goes off? It turns into a 0. When we are reading, we count how many ones we have. 1, 2, 3, 4. 4. That's odd. That's even. That's not odd. And it tells you, hey, something is wrong with this file. Something has changed. I don't know what happened or which bits changed, but it's no longer the same. So just for you to know now that parity is used as a way of maintaining whether a tape is or information stored. Does it have an error? Is it the same as we stored it, or has it been modified? Sometimes, intentionally, sometimes by accident, it just changed. So anyway, information is written 1 byte at a time across the tape, but 1 byte after the other in sequence. So a file that has 1,000 bytes, then it will use 1,000 of those vertical trips. So magnetic tape records data on 8 parallel tracks that run the length of the tapes. Sometimes you'll find 9th one, that's for the parity. That's not part of the data. The parity bit is not part of the actual information. Once you read it and you count and everything is good, get rid of it. It's just a way of letting you know that the data you have is correct data. Okay, density of a tape determines the number of characters. How much information you can store in a tape, it depends on how close it is. So if we have inter-record gap, it's gonna be, not carry a lot. But if blocking was used, that means every 10 records are written together, and then we stop at the end of a block. So they have an inter-block gap. So in tapes, nowadays, they always use blocking. It's more efficient, and you need less trips to the tape. If I say read the entire file, if you have to read it 1 record at a time, read 1 record, stop, read 1 record, stop. It's really slow. But what they do is read 1 block. A block can be 10 records or 100 records, and then go and read the next block. And therefore, every time the tape stops, it needs a bit of space in front of it so it can start spinning again and reach that correct speed for reading. So instead of inter-record gaps, they have inter-block gaps. So an inter-block gap is a gap between blocks. Every block can then gap, and then block. And what's the block, or what's the gap for? It has 2 purposes. It tells you where's the start of the block and where the end of it. But also, when you stop at the end of a block, you want to start reading the next block, it gives you a bit of space for the tape to reach that suitable speed to start reading. Otherwise, you try and read and the tape is at the wrong speed, you won't be reading that much. And the inter-record gap is about 1/2 inch, takes 1/2 inch, which is, you could store a lot of information on a hard disk on 1/2 inch. So that's what tapes look like. And another problem with them, so one problem is that they're sequential. Sequential, that means you have to read them in sequence. And if you miss something, you can't just reverse to it and read it again. No, you have to go back to the very end and start reading until you reach that part. That's the problem with them. Another problem is that you almost need somebody to change the tape. They call it tape mount. Yeah, you need a person. They used to be operators. They call them people that work, and they open the tape and remove that reel and put the other one, and you have to feed it through the little rollers into the next roller, and then starts feeding it, and then starts working. So anyway, this is the difference here between inter-record gap and inter-block gap. So it allows it, with using blocks, you can actually store more information onto a tape because you get rid of a lot of gaps between records. Remember, when here, that's the information in white that's stored, and in gray space, we can't store it. So there's a lot of wasted space if we use inter-record gap. So blocking gives you fewer input-output operations. So instead of reading 100 records, instead of going 100 times to the tape, if you're reading them with records, you have to go 100 times. If you're there blocking, if every block can take 50 records, you only go twice and do 2 trips. But the disadvantage of blocking is the overhead. You need some, program that will be doing the blocking and say, oh, you want 1 record, there it is. And if you ask for another record, it knows it doesn't go to the tape. So you need a little software, but that's not a big issue. But you also need space, you need buffer. So if your program says, read me 1 record, you don't read 100 records, you need place in memory to store them. So you need memory just like the memory we used for the printer, for spooling, to improve the performance. You also, for blocking, you need memory. So memory is so important, and it can make things work much faster. The advantage of magnetic tape, the biggest advantage is it's cheap. Very low cost, the lowest storage way of data, the lowest cost to store information, much cheaper than hard disks and any other form of storage right now. But maybe, things will change in the future. And it's a good medium for backing up magnetic disks for a long time. Well, long time is a little bit debatable. How long can you leave information onto a tape? Does anybody have any videos of yourself when you were a baby? No, maybe you don't, maybe because maybe when you were a baby, there were no digital camera. Well, there were digital cameras, but they were storing information onto tapes. So there are millions of tapes around the world that are now sitting, stored, but you can't really watch them, what's on them. Because remember, when you record something onto a magnetic device, you put a magnetic charge onto it. And with time, this magnetic charge kind of dissipates. It's weaker and weaker. And after about 15 years, 20 years, it disappears. And if it doesn't fully disappear, part of it disappears, part of it do not, so we start having noise. That's why if you listen to an old recording of music from the 50s, you have a lot of noise. If you watch a video, an old video, unless it's been digitized, it has a lot of noise. It's not very clear. Why? It was very clear at the time. Why? Because the magnetism is gone. So you don't have exactly the same data as when it was recorded. And this is true with all magnetic devices. Hard disks that are in your laptop or your desktop or those tapes, they will lose they'll lose their data, and their data will be distorted in about 15 years. So they have a lifetime so far. And that's when we then look at CDs and DVDs, they don't have that problem. So when you put a fresh magnetic charge onto a tape or a hard disk, it will start slowly dying out and it disappears after a while. So that's a problem of all magnetic storage devices. But the other problem with tapes is that because every time you want to read, let's say you kept reading until the end, almost near the end of the tape, and now your application, your user says, I need a record at the start or somewhere in the middle of the tape. Then you have to spin the tape all the way back. It takes a minute or two, or maybe more. And then start reading, might take 5 minutes before you reach that point you want. So there's a lot of delay. Is that good for interactive systems? No, it's not. For interactive systems, you want a long or a short? You want a short response time. Tapes will not be suitable for short response time. They can take a long time. And therefore, they're not good to have them as a program for users to use and interact with, and they want a quick response. They're not suitable for that. And even now, right now, they don't use them for anything that requires quick response. But mostly, they use them for backup. At night, when the company closes down, they have all, or the bank or whoever, in a lot of organizations, they start copying all the data on hard disks and putting it onto tapes, storing it. Why? Because just in case, the place goes on fire or you lose your data or the computer collapses, you have the data. But it's not an interactive thing. At least you have the data. Like some data is so expensive. Like if a bank loses all its data, they pay $1 million to get it back because they lose so much business and so much, information disappeared. So instead of that, they say, okay, let's back it up every night just in case. So at least we have a copy. If something goes wrong, we can copy it back. And maybe we'll never need it. We don't need to copy it back because nothing ever goes wrong. Well, nothing went wrong for a long time. That's fine. But tapes are good for that. Backup. And they can take a lot of information overnight. We're not in great hurry. They might take an hour or 2 hours or 3 hours to copy all our data. Okay, so let's go to what's known as the direct access storage devices, DASD, that's direct access storage device. What does that mean, direct? That means you can go directly to any point as opposed to the tape. See the tape, if you want a point somewhere and 3/4 at the other end of the tape, you have to read until you reach it. You cannot go zoom straight to that one. You need to know how far you went into the tape and read records. Right. Now, these are the direct access devices. These are the ones that you can go to any point at almost the same length of time, almost. With a tape, there could be 10-minute difference between, if the record you want to read is in the front of the tape or at the end of the tape, the start of the tape or the end of it. But with a hard disk, it probably takes 10 millionth of a second or less, the difference between whether it's on this end of the tape or of the hard disk or the other end. There's very, very little difference. And that's why they're called direct access device, that you can go directly to any point at very little difference between them. So it doesn't matter where you store your information, you can still reach it. And they are a lot faster as well than tapes, and therefore hard disks are quite suitable for interactive operations. They have very little response time. And we'll concentrate on those. So the categories. Hard disks as well, they can be divided into the categories of direct access. There are magnetic direct access, there are optical direct access. Optical, that means you use light to write onto them or read from them. That's CDs and DVDs, and Bluetooth and all those ones. And then flash memory and magnetos. We'll talk about more specifically about hard disks, but we'll flash some of the others now. So location of a record directly affects access time. It's still access time, even though we said there's very little difference between them, but that difference we can improve it. So we'll know about that. Now, there's something called the fixed head magnetic disk. That's the one. Let's look first at a hard disk first. So a hard disk, this is a hard disk, for an example of a hard disk. We saw one earlier on. And it has this head here, this arm, this is an arm, and at the end of it, tiny bit, is the head. And that's a wire, an electric wire, go all the way there and comes back. So if you want to record, we send the electricity to generate a magnetic field while this thing is rotating, the disk. And if you want to read from it, this is rotating, it has magnetic charge, it will generate a small current in those wires, and we can read that, is that 1 or a 0. Well, that's really what a hard disk is, and the head just moves towards the center or towards the outside. While the disk is spinning underneath it, so it can access any part. All it has to wait, for example, it wants to read something on this track here, on this circle, this location. So all it has to do, the head, move out there on the same circle or the same track. And this is spinning and wait for it to rotate and get to it. Goes underneath it and will read it. How fast does it rotate? Anybody knows how fast the hard disks rotate at? 1,500.
5,400.
Oh, 5,400. Yeah. But nowadays, they rotate at 15,000 revolutions per minute. 15,000. That's pretty fast. I don't think they can have them much faster than that because, you know, as things spin, they get pulled away. And the faster they spin, the strength of, it's called centrifugal force, is pulling them away. 15,000 revolutions per minute is quite fast. They might go maybe to 20, 25, but there is a limit. You can't just continually spin things faster and faster and faster and faster without, you know, the strength that's required to hold things together. But the heads don't care because they're not spinning. The disk is spinning between two heads, one on top of it and one underneath it. They're not touching, but they're very close to it. Very, very close. That's why they say, don't move. It's a bad idea to move your hard disk, to move your computer when your hard disk is spinning. Do you know why? There's something else. You don't need to know this, but I'll just tell you. If you have something that's spinning, it has something called gyro effect. What's that gyro effect? Gyro effect, if something spins at reasonable speed, it holds this position. If you try to twist it, it will resist you. This is a natural thing, you know, just like magnetism, weight, all these things, gravity. They discovered this, that if you have something that's spinning, and if you try to move it, rotate it in a different direction, it will resist your movement, it'll stay where it is. And that's why they use those as compass in aeroplanes. Aeroplanes don't use magnetic compass. Because magnetic compass is not very accurate in many places. When you go up north, it doesn't know. Over the pole, a magnetic pin always points to the north or the south. Usually north, all right? North-south. But what if it's already on top of the north? Where will it point? So it just spins around. So it's not very accurate, magnetic compass. So what they do, they have, every time you get into an aeroplane, before the airplane starts moving, they start this gyro. And the gyro is just an electric motor that rotates. And once it starts spinning, it holds that direction. So the aeroplane rotates to the left, the gyro is still pointed there. Rotates right, the gyro, once you start it at a certain point, it will never change it until you switch it off. So they use that as a reference and they use it for direction. It's very accurate. But that's what I mean. So the thing about it, if your hard disk is running and spinning at 5,000 or 10,000 or 15,000, and you lift up your laptop and move it, it will try and stay where it is. And if it tries to stay where it is, it might touch the heads. Because the gap, the clearance between the head and that hard disk is so little. And if it touches them, that's it, they're gone. The head is gone, damaged, and the disk is damaged. In many hard disks, when they're not running, they pull the disks away. They say parking, put it in, they go into parking space. So even if you move it in the car and throw your laptop, the disk might move, but the head's already taken away off it. And then when you start working, all the heads go in between the different disks. So, but it's a good idea not to move your hard disk while it's working, your computer. Don't say, copy this file, and it's a video, it's gonna take 3 minutes to copy, and you pick your laptop and start moving. It's not really a great idea for your hard disk. It might cause your hard disk to fail. Okay, so that's what hard disks look like. A lot of these heads, when the heads have certain amount of movement, they only move from the inside closed track here to the outside track. And every time, every position they take, that's one circle. We call it one track. And these tracks are numbered from 0 to the maximum number of tracks. 0 being the track on the outside. So the outside track is always number 0. And that's very important track. Operating systems always are stored on track 0. Track 0, nobody uses it except the operating system. So every time you start your computer, remember, you said there is a little program in memory, not in the RAM, it's in the ROM that is always there. It goes and brings the operating system. Where does it bring it? From the hard disk. Where on the hard disk it goes is going to be on track 0. So it reads that, puts it in memory, and the operating system takes over. But the range of movement is very small. But in this range of movement, you might have 400 different circles, or 4,000 different circles, or 16,000, or the numbers. They're getting so accurate that this head can move a tiny little bit, 1/100th of a millimeter, just to move. And in the older days, they have an electric motor. When you switch electric motor, it starts spinning. When you switch it off, it doesn't stop. It slowly stops. Not very accurate. But the electric motors they have on these discs, they're called stepper motor. They're so special that they go in steps. And they can go, in the older days, they used to go in 100 steps. Then they became more accurate. They go to 1,000 little steps within that maybe 4 centimeter space, or 16,000. So they can actually move so tiny bit of movement to do more tracks. And the more it can move, accurately, the more information you can write, because you can write on each track, on each circle. Now, but hard disks, those hard disks, in order to read information, this disk needs to be spinning. And you get the command. And the file, for example, is going to be stored in a certain place. These are what the tracks look like. They're numbered 0, 1, 2, 3, 4, 5, all the way to the inside track. And every track is divided into smaller sections. They're called sectors or blocks. And that's the blocking. Every time you say, read me 1 byte. If you tell your program, like you're writing on Windows, right? On Word, you're writing a letter or doing your assignment. You write 2 characters. You say, save this file. In fact, the hard disk, the operating system will give you a block. It will not give you 2 bytes to save your file. It only deals with blocks. So the block is the unit of allocation or deallocation. You want a file, you start a new file, you put 1 character in it? No, take a block. The block can be 5,000 characters. So every time you start a file, we give you a block. And then you start filling, write. You fill the block, you want 1 more character to add. It'll give you another block. It can be the next block, it can be another block somewhere else. We'll see how that works. We'll begin the filing system. But on hard disk, that's the unit. When you say read me 1 character, it doesn't go read 1 character, it goes and read a block. It gives you that character. If you want the next character, there, it's there. You don't have to go. Because the hard disks are too slow. Which they are. They are mechanical devices. Now, how do we calculate the performance of a hard disk? Is by how long does it take to read information from a hard disk? Well, how long does it take? Let's say the head is here. And you're told to read that sector there. So the head is not on that track. First, you have to move the head there. So the head moves to be on the same track as the information it's going to read. Right? So that's timing. And it takes 1,000th of a second to move over 1 track. So from here to there, it might take us 20,000ths of a second. Like, And then on top of it, now that's it there. It's spinning at 10, 15,000 revolutions. So it has to wait for that part to come underneath the head. That's also another very fast. So it's moving the head, and that's called seek time. Seek is the length of time it takes to move the head to the required track. Once we moved it, we wait for this. This is called rotation time. How long will it take? You could be lucky, and that required could be here, so it can be even shorter. You could be unlucky, you just missed it, so you have to wait almost for a full term. I think the full term is going to be, there's going to be very little difference between them. But these are two parts. And then the final part, once this goes under the head like this, just spins underneath it. The information is picked. So there are 3 times in order to evaluate the performance of a hard disk. 3 time delays: seek time, rotation time, and transfer time, or read or write time. And the longest is the seek. This head that moves between tracks is the longest. So some companies, they said, no, that's too long, it takes too long. So what they did, they said, forget about the moving head. Let's have a hard disk that has fixed heads. What do they mean? So you have a hard disk, and on top of every track, you have a head installed. If you need to, you might have put them there. So, but there is a head sitting on top of every track. So when you say read, you already have the head on top of the track. So you've eliminated the longest delay of a read from a hard disk. Even though when you say longest delay, you've eliminated 2 or 3 thousandths of a second, 3 thousandths of a second. But they call these the fixed head. They're the fastest reading hard disks. They're only used on airplanes, spaceships, anything that requires much quicker response. They're very expensive and very difficult to make. And you need one head for every track. Instead of having one head covering the entire surface, you can go, but with a bit of a delay. So they call this the fixed head. So the usual question, which one is better, a fixed head or a moving head? The fixed head. Did you say fixed head or moving head? Fixed head, yeah. Yeah. What do you think? Fixed head or a moving head? What do you think? Which one is better? You're offered this, and we're going to give you a hard disk on your machine. Would you like a fixed head or a moving head? She said fixed head would be a preference. What do you think? Huh? Moving? Why? Okay, a little bit slower. What do you think? Yeah? It depends, guys, it depends. At this stage, you should never, ever in technology, guys, make one option over the other. Never. If they ask you in any place, don't put yourself in a hole that you cannot come out of. If they ever ask you, is it better to take this computer or this computer, don't say this one is better. Because it looks faster, maybe. Yeah, but it's probably more expensive. And that's exactly in this case. They ask you, do you want a hard disk fixed head or a moving head? If you say fixed head, you might have to pay 100,000 euros for it. If you want a variable head, you might have, 1,000 euros. So it's good, it's fast, yes, it's better. So it depends. If you're looking for speed, yes, fixed head is much better. If you're talking about cost, if your company says we're going to buy 20 hard disks or 100 hard disks, so we buy this or this, and you tell them buy fixed head, and then the company goes bust. If they sign a contract to buy it, they don't even have the money for that, and then they blame you. So you ask them, if you're looking for cost, well, go for the cheaper one. Anyway, let's go. Let's keep going. So be careful, guys. So the movable head magnetic disks have one read and write head, and it just goes to the correct one. And disk packs, those disks that you see, it's not worth having a hard disk just with one disk, one round disk. Or they take a few of them and stack them one on top of the other. And each one of them, you need to know these names. They have tracks. So a lot of the times you can't see them. You barely see them as a shape. They're not, they don't drill them. They're not kind of notches in the tape. They're magnetic, that's all, magnetic charge. In fact, sometimes they look slightly different in shape, but you can't actually all the time see them. So these tracks, it depends where the head stops and starts writing, that's the track. So we have tracks on each side, the tracks on this side and that tracks on the other side. And the tracks are on the same distance as well. So track, say, 10 is right on top of track 10 on the other side, exactly. So with the two heads, there's a head on top of the disc, and so as the head spins underneath, as the disc spins underneath the head, there's also another head on the other side. So as it's spinning, you can read from the top head or from the bottom head. And also you have another disc here with two more heads, another disc. So at any position, any moment, all these arms with the heads, they're all on the same track on their own individual sides. So if you're reading track number 10 at the top, you're also reading track number 10 at the bottom of that disc, and also number 10 on disc number 2, disc number 3 and 4 and all that. And you can move all the heads together to track 40 or track 400, move back. So every time you move one head, they're all moved together, and you can read all the way. So this is not just one arm here, there's another one underneath it that has one head for the higher disc and one separate head for the bottom disc. There's different head on each disc. And the head is more or less something like this. It has an electromagnetic kind of device that if you want to write 1 or 0, we send current this way around this to generate a magnetic field, and it magnetizes the surface. This part of the surface that can be magnetized. Remember, not the whole disc is made of iron. The disc itself might be made of another material, but just slight thin surface on the top that can be magnetized. And that's the one. Whether it's tape or magnet, that's the same reed. And this is the right head. And beside it, there is another reed head. And the reed head is just a wire. Remember, if you put a magnetic field on this, there'll be a magnetism here. If this goes over it, it will touch this wire, it will cause a small current to go on this wire, and that's how we read it. So the head has those two together. One little coil for reading and one little coil for writing. And probably all it does is just turns the north and south this way or this way for 1 or 0. So that's how we recognize this 1 or a 0. Any questions so far? So this is how, a nice kind of image that shows how a hard disk is spins. Of course, will be spinning at much faster rate. You can hardly even see it spinning. And the arm just moves from track 0 on the outside to track there, and just goes to wherever the operating system say, go to track 400, go to track 200, and read from sector 3. So everything stored on a hard disk is given a track number and a sector number. And then we'll get down to, or a block number. And that's what the head might look like, but this is kind of, these are these two plastic things here, but the read or write heads. But therefore, and the disk is going between them. So one of them is for writing on the top part of the disk, and one for the bottom part of the disk. So you can have a look at those, but we don't need to go into the structure. That's engineering, if you want to go into engineering, how they make it. But that's how close they can be. They're very, very close to the actual disks. So you can see here, the gray part here is the disk. And on top of it, there's head number 0, head number 1, head number 2, head number 3. They're almost touching, but they're not touching the actual disk. So disk has to be well balanced, it has to rotate perfectly, and it must never touch the head. If it touches the head at that speed, it will burn it, it will cause a huge. That's why you shouldn't move the laptop when the head is spinning, when the hard disk is spinning. The head doesn't spin. Okay, so this is the way things are. So if you want to read from particular information from a particular place, you need to know which track it's on. So that's what a track is. And every track is divided into many sectors. So that's a sector. But if they went even further and said, okay, let's take a few sectors, 3 sectors or 4, we call them a cluster. And there's another unit. But the block or the sector is the unit. The cluster is just a few blocks or a few sectors. And if the heads, guys, go to a particular location, let's say go to track number 10, all heads can read from their respective track number 10. They call this a cylinder. So a cylinder is not a real cylinder, but it means the same track numbers on all disks. Wherever the heads happen to be, they're on 400, you say that's sector cylinder 400. So if you're asked, what's cylinder 400? You say all the tracks number 400 on that package of hard disk, on all the surfaces. All the tracks that have the same number are called the cylinder. So this is what a track, a sector, and a cluster might look like. See in blue here, the whole thing, we call it a track. And the track is divided into smaller units, there, here, there. Second. And something else to notice, when you write so many bits here. Now, the same number of bits you write here is the same number of bits you write on the inside track. So if you can write 4,000 bits here, then also here we write 4,000 bits. But of course, on the outside, it's a bigger circle. So it's going to be more spaced out than inside the track. So they can actually write, even here, they should write maybe, I don't know, if they can write 1,000 here, they might be able to write 5,000 here. Why don't they do it? Because it's too complicated then. It's easier this way. Because we deal with the hard disk with circuits, with angles, rather than length. We don't need how long space we're going to have to write on. They just say, okay, rotate it quarter of a turn, and that brings you. So whether the head is here or there, read the same amount of information. Newer hard disks, they started actually writing more information on the outside track, and they deal with this problem, the extra complexity they have. One other thing that you need to know is that when the hard disk, when the head moves to this track, sometimes it's over, goes a little bit over the limit. So now they have space between this track and that track and that track. Remember, like with the blocks, the inter-block gap or inter-record gap, also here they have inter-track gap. So there's a bit of gap between every 2 tracks. So the head can realign itself, for example, it knows if it's just done over the edge, and it doesn't start reading from the next track. So there's a little bit of a gap or a space between tracks, and they call them inter-record tracks. And they also have, even when they divide a track, this track, say the outside track here, into sectors, they number these sectors, sector 1, 2, 3, 4, 5, 6. And also for the hard disk to start reading, it will read, and when it reaches the end of the sector or the block, there's a gap there. So they call this intersector gap. Intertrack gap. I'm just about to start. Come on in, waiting for you. Good morning to you. Right, let's start. So this is, if you want to look at a hard disk, are you okay? Yeah.
Yeah, I'm okay.
Good. Right, so this is what kind of you might not see, but that's what the reality is. So these are the tracks, and between every track and the next, well, these are the tracks here, this part here. And between that track and that track, there is a gap. And these are the sectors going from one, and this is a sector gap. And where is track number 0? Any idea where track number 0 is? Is it this track here? Or this track here? The outside track is track number 0, guys. Right? If you were listening to me, I probably mentioned this. Okay. This is for your information. You don't have to learn it or remember it, but it's good to know it. These are the units used for storage capacity. I will not be asking you what's a kilobyte or what's a mega or whatever, but here it is. So if you hear, you buy a hard disk, they tell you this is a terabyte hard disk. How much is a terabyte? It's 1,000 megabyte. And what's a megabyte? Or sorry, it's a gigabyte. Now what's a gigabyte? 1,000 megabyte. So a terabyte is a billion. So it's good to know those. Bit, byte, and you go into kilobyte, megabyte. Megabyte is 1,000,000, gigabyte is 1,000 million. That's a billion. It depends on, and terabyte is 1,000 guys. So they all go into extra 1,000. So every time you store information on a hard disk, you need those 3 pieces of information to locate it. You need to know the hard disk will have a pack. Like it will have multiple disks. This one has 2 disks. This is now looking at it not from the top but from the side. You can see that the heads here barely almost there on the surface. This one here has 2 disks. Surface 0 is the top one. This is surface 1. Surface 2, surface 3, surface 4, 5, and you keep going. So if you have a file stored on surface 2, that means this one here, this surface. Now you need to know which track. You need to have the track number, and then you need to have the sector number. So every time a command is given to the hard disk, to go and read or write, you're given 3 numbers. Which surface, which track, which sector. Well, that's said, right? I don't read that. And it always reads that. And we call it sector or block. If you call it block, it's okay as well. So you can read or write. And if you had one big file, huge file, is it better to give it a file that needs, say, 8 tracks? Is it better to give it 8 tracks on the same surface? Or is it better to give it 1 track on this surface, 1 track on that, 1 track on there, 1 track on there? You go to different surfaces with 1 track on each one of those surfaces, or you give the same surface, you give 4 tracks on the same surface. Remember, every time you want to read 1 track, you have to move the head to that track. And that's the longest delay, is moving the head to that track. So, if you had the file on 4 separate tracks here, if you have 4 tracks, then you go to 1 track, read, then you have to move the head to the next one, then the next one. So you have 4 seek movements. That's the longest delay is good. Remember, we said the total time of read is moving the head to the right track, waiting for the sector to go under the head and then pick up the information. The longest of those is moving the head. So if we have a file that needs 4 tracks and you put it on the same surface, then you have to move the head 4 times to read the full file. If we can put the file on the same cylinder, what does cylinder mean? Anybody remembers what is a cylinder on a hard disk? Do you remember?
Storage reduction.
Okay, anybody can define it slightly better? What's a cylinder on a hard disk? What's cylinder number 12? All tracks that have number 12. One of them, say number 12 on this surface, 12 on the other surface, 12. So the heads are always on the same cylinder. So if we give the same tracks like for a file, so now we only move the heads there to start reading from the first one, then we don't have to move it to read the bottom part. So if we write a file without having to move the head, that would be much better, much faster. This is just for a piece of information. So just keep it in mind, the less seek time, the less we have to move the heads, the better. That's what it might look like in a very bad representation, but you have an idea. So you have multiple heads. The part in the middle they call the spindle, the part that has little bearings that allow it to rotate. Is a vertical kind of column that holds all these discs together with bearings. They call that the spindle. We don't need to really know about that. But what you need to know is a track, a sector, and a cluster. So these are the 3 main parts. You need to know the surfaces, that a hard disk may have multiple disks, and they're given numbers. Number 0 is the top surface. Number 1 is the lower, the one underneath it immediately. Number 2 is the next disk, and so on. So numbering is important. And the tracks are given numbers from 0 to the maximum number of track, 0 being the outside track. Now, you have enough information on hard disk. Which one is better now, hard disk or a tape? A tape. It's a good answer. That's the wrong answer. It depends, thank you. That's a brilliant answer. Now, give me one reason why she said tape is better. Let's handle that. You tell me why a hard disk is better. Yeah? Okay, what about hard disk? It's fast but expensive. It's the opposite of that. Yeah. Any other differences? Any other advantage of a hard disk over a tape? Are you sure? Okay, I'm sure we can have 2 tapes. Like quantity, we can store a lot of information on both. Which one stores more? How do you measure it? You measure by cost, money. Which one is going to be cheaper? Tapes. Like you can have 10 tapes, and for the same amount that they charge the cost, they'd be a lot cheaper than the hard disks we need to do the same job. Any other advantage of hard disk? What's the main advantage of hard disks over tapes? Sorry? Yeah. Is there a nice technical name for that? It's called direct access device. What does direct access device mean? What's a direct access device as opposed to sequential access device? At reasonably high speed, as opposed to the tape. The tape also can go to any point, but take a long time, very long time. With the hard disk, the difference between any 2 points is minute. With the tape, the difference between a point at the start of the tape or at the end of the tape can actually take 10 minutes or an hour even, depending on how long the tape is and how fast it is. Oh, we haven't gone through halfway yet. Okay, guys, quick on CDs and DVDs. Everybody recognizes this, right? Anybody can tell me anything about it? You probably all know about it. As a storage device. Okay?
You can store more.
You can store.
In same quantity, you can store more than CD.
You can store more on a CD than on what?
DVD. In the DVD, you can store more than also.
Yeah, okay. Now we're talking about both of them together as being optical devices. Why do they call them optical devices? Because the word optical means light, and we use light to store information here. We actually use laser. And in fact, we burn the surface of the device. In the case of those CDs and DVDs, we actually burn a hole in there, in the surface. So the surface is so smooth, and we shoot it with a laser to represent 1 or 0. And then, if we want to read it, we use the same laser, but not the same strength, like light. We flash a light on it, and it will reflect. If there's a hole, it'll reflect in one direction. If it's a surface, it'll just hit and go in a different direction, so we can read whether it's 1 or 0. Well, the idea is so simple. So, a CD, let me just go. A CD is a device that's made up of plastic most of the time, simple plastic. And they cover it with some metal, right? They cover it with some material that can be burnt easily. So they mix a couple of metals until they found something that can easily be burnt by a laser, and once it's burnt and cools, it holds that position. Now we can shine a light on it and see, does it reflect it back or does it go somewhere else, and we can say it's 1 or 0. Well, that's the basic idea in CDs. And therefore, is it better? How long will the information stay on a CD? Will it stay longer than a hard disk or shorter time? Longer. Why? Why longer? Why is it shorter on the hard disk? No, this one rotates as well. So you mean a hard disk can lose its information if it rotates? No, that doesn't happen on hard disks. Why are hard disks? They keep information for shorter time.
Because hard disk we use magnetism, so if you lose the magnetism.
Exactly, because hard disk, guys, a hard disk uses a magnetic charge. We put magnetism onto the hard disk to store information, whether it's 1 or 0. And this magnetic charge gets weaker and weaker with time. It's just you lose it slowly over a period of maybe 15 years. That's why I asked you guys if you have any videos of you and your kids. Because maybe your parents loved you so much, I don't understand why, but they might have taken a lot of videos of you. They're absolutely delighted with you. But those tapes, if they have not transferred them onto another, storage device, they'd be gone. They'd be not clear by now. Most likely, you won't be able to see half of those tapes, or half the amount on each tape, because the magnetism will disappear if they use magnetic. Then around the 2000, maybe 2000, the other cameras came up with magnetic tapes. Yeah, they're still magnetic tapes, but at least they're digitized, and they can go straight onto a computer that you can copy them onto a hard disk and somewhere else, and keep copying them. If you take a hard disk and you say there's a lot of great information on this, I want to keep it, and you lock it up, it won't be on it in 15 years. So I just want you to know that. And that's the reason why a lot of television companies and music companies, they're digitizing. Why do you think they're digitizing? Because they are losing all that information. All the music that was recorded more than 20 years ago, it's of no good now, unless they have digitized it. And when they digitize it, then they can copy it and copy it again. How do you say close the door in Chinese?
She's Korean.
Huh? Okay, now is there any difference between a DVD and a CD? Or, sorry, is there any difference between a CD and a hard disk, the way we store information? Okay, this is a hard disk. Information is stored on tracks, and the tracks are circles. One circle inside the other. They call them concentric circles. Small circle and another circle bigger than it. They don't touch one another, the circles. That's on hard disks. And then we divide every track into equal size sectors. So they look something like this. Now, the CD and the DVD, they have tracks as well, but they are not circles. One line, one continuous line. So they go around in spiral. So it starts, as you can see, I'm going over the same track of the same line, and it keeps getting bigger and bigger and bigger. So it's one continuous track that spirals around, either from the inside or outside. So we can't say track number 1, track number 2, it doesn't make much difference. But this is also divided in sectors. And the sectors are of equal length. Remember the sectors here. That sector on the outside there are of equal length, but the one on the inside are much shorter. On a CD or a DVD, the length, the actual distance length is the same. They're all the same. So see, this track goes all this length until here. So it went a circle and a half maybe. Well, the track on the outside, it only goes that way, but they're the same length. So this is distance. They are equal in distances. On the hard disk, they are equal in angles. So it's angular. So as this one rotates, for example, 10 degrees, there it is. Or they are all another 10 degrees, they're completely different track. So they're not equal in distance, they're equal in angular equality. While this one here, equal in distance. So the tracks are a little bit kind of off, But what does this mean? It means you can write the same information on the outside as on the inside. Remember, with a hard disk, we said, for example, if you can write 10,000 on the inside track, or 100,000, you also write 100,000 on the outside track, just more spaced out. No, on a hard disk, on a CD and DVD, you can write more. You can the same density. So you can actually, even though on a sector it's the same amount of data, but you're going to have more sectors. While the inside circle is all one sector, possibly, and even not even one sector. But here you might have 5 or 10 sectors. So all information is condensed at the same level, whether near the center or away from the center. So you can actually put more information onto the CDs and DVDs than you can put on a hard disk. But they've started recently, only last year, the year before, a company came up and said, no, okay, there's too much wasted space there, too spaced out. I'm going to condense them, and I'm going to use the same idea as on hard disk within reason. But they still have concentric circles, but this circle on the outside, they split it into more tracks. For example, this one has 10 tracks, this here might have 30 tracks on the outside. So, but we're still, the majority now of hard disks are like the one we have at the moment. They have the same sector, not the same density, the same amount of information. But on CDs, on the outside track, you can write a lot more because they have the same density. So this is what a hard disk tracks look like. They're called concentric circles. And this is what a CD looks like. The track is just one track that spirals out or in. Now this is the new hard disks. They said, hey, there's a lot of wasted space. We're going to put more tracks on the outside, more sectors on the outside tracks. Now, the same amount of information you put in a sector is the same, now the same length, but it just means we're going to have more sectors and we can store more information. So modern kind of hard disks. I don't know if it's catching up with all manufacturers or not, but definitely they can store more information. Right, so you can read the rest of the information. It's just general information for the rest of it. Okay, for CDs. That's what a CD looks like. It has a laser, and the disk is rotating underneath it. And the laser, every time you want to write, it shoots a laser at the surface, and it will burn the CD or the DVD. There it is. It just burns a hole onto the surface. And when you want to read it, see the holes, they call them pits. So the pit is a big hole in there. Of course, this is made much bigger. And this is a CD with spaced out. Then, like everything else, with time, they perfected it and they can actually have more surface. But that's, if you look at the surface under a telescope or, under magnifying, with some magnification, you'll see a lot of holes in following a particular line. A hole means 1 or a 0 and vice versa. But then, that's why CDs, you can only read them once. You burn it once and that's it. But then they started mixing different material that you can actually remelt it. And when you melt it, it goes flat again and you can burn it again. And they call these the rewritable CDs. So when they came up with the rewritable CDs, just the material on the surface is slightly different. They mixed other materials, so now they can actually melt it all and start writing on it again. When they melt it all melts, goes flat, then cools down, and then we run it again, we start burning a particular spots. And they call these the rewritable CDs. Because initially when they came out first, you burn it, you can never rewrite on it. But no, we can now rewrite on them. But you can rewrite on them, they say forever, but that's not true. They found that there's a limit of 100 times rewriting onto a CD. And then they found that, yes, they claim that they will live forever. If you put them in the correct environment, store them and lock them up, information is never lost. They found actually it does get lost because of another phenomenon. See, this surface that they put on top of the plastic thing for CDs and DVDs is made up of many different metals, many different materials. And when you mix two different metals together and they're in contact with each other, there's another, natural thing that happens. Anybody knows what it is? Engineering people would know it. If you take any two different metals and just put them one on top of the other and leave them, they will rust. They call it dissimilar metal rusting. So metals can actually rust if they touch another metal of a different kind of metal, and different ones will rust at different rates, touching different. I don't know. It has to be maybe the nuclear and the electrons in both materials. They start rusting away. So because those surfaces are made up of different metals, they realized that they found that, the data is there, but suddenly the whole thing has disintegrated. It started rusting away. So that's not that statement that they made once that they're there yet, they can hold your data forever, is not correct. They actually rust away within the space of about 10 to 15 years as well. So they might improve it. And once you burn the surface, you can actually see the slight different shade because of the burning on the tracks. And this is maybe the same tracks, but on a DVD rather than a CD. So they're a lot closer together and they're more controlled. Well, that's what maybe a CD looks like if you are inside the device and spinning underneath you with the laser is shining. Just lots of pits and lots of flats. That indicates ones and zeros. And so that's a CD on the top left. They came up first and it can store 700 megabytes, and then a DVD that can store 4.7 gigabyte, slightly closer together, more condensed, and DVD, high density DVD, that's 15 gigabyte, they're available now, and the Blu-ray that can take 25 gigabyte. So it's an amazing amount of information, but hard disks weren't even going near that, but now hard disks are also improving tremendously. Now, the laser is too much, too strong, so some companies came up with an idea, let's use magnetism, but also with laser. So we don't need as much laser. Laser will actually drill a hole, will burn a hole. But they say, okay, if we have a lighter laser, they'll just heat it up a little bit, and then magnetism can have a better, it can absorb magnetism and hold on to it better. And they call these magnetos. They call them magnetos, these devices. Another form of storing information using magnets and using laser. I don't know how successful they are. I haven't seen many of them. Then another storage medium is the flash memory storage. That's your USB. That's another form of storage. That's electronic, fully electronic, no moving parts, and it's just full of millions of switches, and you can switch them on or off and they'll hold their position. They're not like RAM, like memory. When you power down, you lose everything. You know, with this one, when you switch, it's like light switches. You switch it on, it stays on. You switch it off, it stays off. That's what USB is. And it's millions of those switches, or billions of them, and they're in a little small space. And they're getting bigger. The capacity is getting bigger and bigger, and they're improving. Now, anybody knows what seek time is? What's meant by seek time? Come on, don't sleep on me, guys. What's seek time? Any idea? Seek time? Yeah. You sure? Okay. You know seek time, right? Huh? Oh, you came in like, oh, sorry, okay. But I mentioned, okay, yeah.
When a pointer changes its position from track 0 throughout to track 12 or something, the time it takes for the system.
Thank you. It's the time it takes to move the head to the required track. So your head, for example, is now at track 300, you want to go to 450, you move it to 450. How long did it take to jump from this location, from the present location? So that's called seek time, and that's the longest delay on a hard disk. And then we have something called rotation time or search time. Anybody knows what's that? What's rotation time on a hard disk when we are reading? Any idea? Rotation time. So now I want to read some information that's on track number 500, sector number 5. So first I move the head to track 500. That's seek time. The next time it takes, we call it seek time. Now what's rotation time? Anybody elaborate? Pardon? It's the time it takes that sector. Like for example, I move the head here, but remember the disc is spinning under the head. Now, maybe when they move the head here, the sector is there. I just missed it. So now I have to wait for it to move until it comes under the head. That's called rotation time. So there are two movements that will take time. And then finally, as that piece of information in the sector moves under the head, it will be picked up, and that's called transfer time. So these are the 3 times. Transfer time is the shortest of them all. So first thing, you move the head from this location to where you want it to be, and then you want to read this sector, so you have to wait for this to go under the head, and that's called the rotation time. Okay. Okay, I thought we'd finish today, but Friday there are no lectures. As far as I know, I heard there is a holiday. Is it true?
Yeah, it's like Easter. Easter, right? Oh, Passport.
Yeah, Friday and Monday. I was told. Now, I'm not sure. You have to check. If it's an official holiday, there'll be no lecture. If there is, if it's not an official holiday, then there will be a lecture. Now I'm going to stop at this point because now we're going to start looking at this. This is what we're going to be looking at next week. This is how it moves. And is it better to read, say, the red part first, like a file is on the red sector here, and another one on the page sector? If you are the desk manager, will you read the red one first or the
Yellow
page one first? Well, maybe. Okay, I'll show it to you quickly. Here we go. Okay. Now, will we read the red first or the green first?
Red.
Well, red. See, this one has red, both of them. Red. Now start again. Red and then went to the green. So it had a bit of space or a bit of time to move to where the green is. Sometimes it misses it. Sometimes. So yes, in this case, yeah, the red first and okay. But we'll see it next week. We'll look at the details. Now, let me take the attendance, guys. I'll run the attendance. I don't know, does it work without me running the app? Let me do something here. Stop the recording.